Okay, now that we've practiced doing some calculus, how to do integration, and we reviewed doing differentiation, and remember integration is the same thing as anti-differentiation, we can continue on with this idea of air resistance. Air resistance is a velocity-dependent force. Sometimes it's dependent upon velocity to the first power, and sometimes it's to the second power. It just depends upon the situation. If it's to the second power, it's more of a drag, whereas if it's the first power, then it's more of a resistant, like moving through oil or something. So in this case, we have something that's, is going to the first power. So imagine a small piece of styrofoam packing materials dropped from a height of 2 meters above the floor. After about 0.5 meters, the styrofoam effectively reaches its terminal speed and then takes 5 seconds more to reach the ground. The drag force is proportional to the speed and is given by D equals BMV. So this would be the free body diagram for in the first 0.5 meters, something like this, somewhere in that 0.5 meters. After the 0.5 meters, then the drag is equal to the weight since it has reached terminal speed. But in the region up here, the net force would be given as W minus D. And of course, F net is equal to MA, weight is equal to mg, and the drag force is bmv. We can divide both sides by m, and we get the acceleration is equal to the gravitational field strength minus bv. Now, after the 0.5 meters, the acceleration is 0. It's reached terminal velocity. So we can go ahead and plug that in, and v in this case would be terminal velocity. And so we find out that the terminal velocity is equal to the ratio of the gravitational field strength divided by this constant, this drag constant B. Now let's go ahead and figure out what this drag constant is. We can do some kinematics to figure out the terminal speed because it tells us it takes 5 seconds more to reach the ground, and it's traveling 1.5 meters. So we could figure out that terminal speed. We also know that what the gravitational field strength is. We could solve this for B, and we get 33.3 seconds to the negative first. So now let's figure out the acceleration at t equals 0. This is right when we first drop it. Well, when you first drop it, the velocity is 0. So we can plug that in, and we find out that the acceleration is that of gravity, 10 meters per second each second. Let's figure out, though, what the acceleration is when the speed is 0.15 meters per second. Again, we can plug this into our relationship of A equals G minus BV that we got from our free body diagram. And we get acceleration is 5 meters per second each second. Let's look at another case where something's dropping through some viscous medium like honey or oil or something like that. We have this 9 kilogram object dropped from rest. The drag force is equal to BV, where V is the velocity of the object, and the object reaches 1/2 of its terminal speed in 5.54 seconds. So again, the free body diagram before it reaches its terminal speed looks like this, where the drag is a little bit less than the weight. Once it reaches the terminal speed, the drag will be the same as the weight and the acceleration 0. So the net force would be given by W minus D. Plug in the mathematical models for F net and for weight, and plug in the drag is equal to BV. Divide both sides by mass, and we find the acceleration is equal to G minus B over M times V. Let's determine the drag coefficient B. Well, once it reaches its terminal speed, the acceleration is 0. And so therefore we know that mg divided by b is equal to the terminal speed. And let's set that aside for right now. We also know that acceleration is the time rate of change of velocity, dv over dt. Notice I'm using lowercase deltas. That's because I'm going to be using calculus here. Now you need to think back, what type of functions, when you take the derivative of them, give you the same function? Notice that I have dv divided by dt, the derivative, the slope of some graph, gives you the same graph again. There's a v here. There are only a few like that. So we're going to see which one it is here in a second. So I'm going to do some kind of funky math over here on the right hand side. I'm going to factor out a negative b over m, and that makes this a positive v. Seems kind of strange to do that because there's not a b over m here, but I can multiply the g by negative m over b, and it's the same thing as what I have up above, and there's a reason why I'm doing this. I'm going to divide both sides by what I have in parentheses here, and I'm going to multiply both sides by the dt. And when I do that, it kind of looks like this. Why did I do that? Well, it's because I needed to get the v over here on the same side with the dv, because I'm going to integrate both sides. Remember, integration is a summing up, or it's the antiderivative. So I'm going to be summing up from 0 to some velocity vt in a time of t. So it starts at rest at time 0 and goes to some speed vt at t. Now on the right hand side, this is going to be pretty easy to integrate because there's no t here, so it's t to the 0th power, so it's going to become t to the 1st power. This is more challenging over here. I'm going to kind of ignore the negative mg over b because notice I'm integrating with respect to v. So this right here is a dummy variable that tells me what to concentrate on. I'm concentrating on the v down here in the denominator. There's no v here. So you have to remember that what's the antiderivative of 1 over x? Because that's kind of what this is like. And if you remember, that's actually equal to the natural log. So I have natural log of, and notice now I'm plugging in the vt and the 0. So natural log of vt minus mg over b, there's no variable with it, no variable v, excuse me, minus the natural log of, now I'm plugging 0 in for the v. Notice on the other side, here I integrated and I got t, because it was t to the 0, now it becomes t to the 1st power, and I'm plugging in the limits from 0 to t. So for the one I have 0 and the other one I have t. So on the right hand side, like I said, that became pretty easy. On the left hand side, it's a little messier because remember that subtracting natural log is the same thing as dividing what's inside the parentheses here, and then taking the natural log of it. Okay, this is really nasty. How can I get rid of the natural log? Well, I can exponentiate both sides. And so that gets rid of the natural log on the left hand side and becomes e to the negative b over m times t. And now I'm going to multiply both sides by the denominator to make it look a little nicer. And I'm going to add mg over b to both sides. And finally, I can factor out the mg over b. So now I get the velocity is equal to mg over b minus, or times the quantity 1 minus e to the negative bm over t. If you remember early on, I asked you, can you think of some function that when you take the derivative, when you find the slope of this graph, you get the same graph again? I'm hoping you remember that that was the exponential function, e. Okay, so now I want to determine the drag coefficient b. That's why I'm doing all this work. Okay, well, it tells us that at 5.54 seconds, we reach 1/2 the terminal speed. Terminal speed is mg over b. So I'm going to plug in 5.54 seconds, and that would be 1/2 that terminal speed. Notice the mg over b cancels. I can rearrange this. And now I can take the natural log of both sides to get rid of the exponential e, and I get negative 5.54 b over 9 equals natural log of half. And now just simply solve for b, and I get b to be 1.126 kilograms per second. Okay, so now let's determine the terminal speed. Well, the terminal speed is mg over b, so I can plug in the mass, g, and now this b, and I find out the terminal speed is 79.9 meters per second. Okay, now let's figure out what time is the speed of the object 3/4 of the terminal speed. Well, now I'm going to plug in 3/4 of the terminal speed, where terminal speed is mg over b. So it's going to be 3/4 of mg over b. Divide both sides by mg over b. Rearrange it slightly. Take the natural log of both sides. And then finally solve for t. And I get 11.1 seconds. Okay, well, let's figure out how far it has moved in the first 5.54 seconds. Well, if the speed is given as mg over b minus mg over b times e to the negative b over m times t, remember that velocity is the time rate of change of position. So delta x over delta t, that's a slope. In other words, velocity is the slope of the position time graph. If I want to figure out what the displacement is, how far it's moved, I need to find the area under the velocity time graph. So I need to integrate or do the antiderivative. So I'm going to multiply both sides by dt, because notice there's a t over on this side, and that means I'm going to have to integrate it, differentiate both sides, from 0 to some position xt at time t. Notice there's no t with this first one here, so it's really t to the 0 power. And so that becomes mg over b times t to the first power now. And for this, remember that when you take the derivative of e to the negative, or excuse me, e to the t, it just becomes e to the t again. Well, this is e to the negative b over mt, so I need to multiply the coefficient here by the reciprocal of the coefficient of the t. So that would be, instead of b over m, it's going to be negative m over b times the original coefficient, which gives me m squared g over b squared. I'm going to plug in t and 0. And now I can go ahead and plug in the time of 5.54 seconds to evaluate it. And now it's just plug and chug. And I get, after 5.54 seconds, it has traveled 123.4 meters.